Alright, we're going to race through a quick discussion of the periodic table. The periodic table was originally developed by a chemist named Mendeleev. What Mendeleev did was he took all the elements known at the time and made a long list of them in order of increasing mass. He then snaked this long list of elements in order of increasing atomic mass, and snaked the list in such a fashion that elements with the same chemical properties wound up in the same column. So what we see when we look at Mendeleev's periodic table, which is what you're looking at now, we see something organized in order of increasing atomic mass, and we see that elements in the same column have the same chemical properties. Mendeleev was so proud of his system and so convinced that he had organized the elements correctly that he even predicted the existence of an element below aluminum and an element below silicon with a mass of 68 and 72 that weren't yet discovered or weren't yet known. And he was, of course, right. Those missing elements being gallium and germanium. The periodic table since then has grown, as we've discovered, and organized more and more elements. Also, another change from his periodic table to the periodic table we see today is Mendeleev organized his periodic table by mass. Today, it's organized by atomic number. Today, the periodic table is organized by increasing atomic number. What is atomic number? Well, that's something we're getting ready to talk about. But be aware that that's the big difference between Mendeleev's periodic table and what you use in your class today. He organized it by mass. We in the modern world organize it by atomic number. The periodic table is organized into rows and columns. We refer to the columns as groups. In other words, this would be a group, this would be a group, this would be a group, this one, this one, this one, this one, this one. Columns are groups. We call the rows periods. We have very simple ways of referring to periods and groups. We name groups using two different systems. The first system is a very boring way, and it doesn't provide a lot of information to us in terms of the properties of elements. This system uses numbers 1 through 18 to number the groups, starting left to right like you would read. This is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the groups are numbered 1 through 18, left to right. Chemistry's easy, life is hard, right? The second numbering system is one that we'll actually use quite a bit in terms of helping us talk about the chemical properties of elements. And that's a system that numbers the groups in what are known as the main blocks, or the representative elements, with numbers and the letter A. First of all, what do I mean when I say the representative block? You'll notice this periodic chart almost exists at two levels. That you have a raised level, and then you have a sunken level. The representative groups are in this raised level. So when I say representative elements, I'm talking about the groups that I just circled there in red. These representative groups are numbered, again, left to right, 1 through 8. With the letter A. So it would be 1A, 2A, 3A, 4A, 5A, 6A, 7A, 8A. And that's how we identify those representative group elements. Now we identify the transition elements, and the transition elements is this sunken group down here. This sunken group down here is identified using the letter B and another number. you'll notice that these numbers aren't mathematical like you saw up there. Here you're looking at 1b, 2b, 3b, 4b, 5b, 6b, 7b, and then all of these are referred to as 8b. We'll explain the logic behind that later. Right now you just need to be aware of the two numbering systems. Also, while we only talk about there being 18 groups, in reality there are 32 groups. These two sunken blocks down here, referred to as the inner transition metals, are their own groups, their own group numbers, and they are, each one of those is a two-member group. So really, you'll hear chemistry refer to there being 32 groups. However, most of the time we're only going to deal with the chemistry of the main 18. Periods, or rows, are numbered much more logically. Periods or rows are simply numbered starting at the top, 1 to 7. It's important to note a couple things about this 1 to 7 numbering system. First, a common mistake people make on exams is they overlook the first period. The first period, or the first row, consists only of hydrogen and helium. So when you're counting your periods, don't forget to start with your hydrogen at 1. These guys down here are not their own periods. This row right here, if you follow the little ray there, belongs between lanthanum and hafnium. So this here is actually part of the 6th row, or the 6th period. There's just not room to write them on the periodic chart there. Also, this row right here fits right in there. So that's actually part of the 7th row. One final note, I have seen periodic tables that will actually start these rows with lanthanum and actinium, but those are a minority of the periodic tables out there. So there are 7 periods, 1, 2, 3, 4, 5, 6, 7. This numbering system of periods and groups allows us to do a couple things. First, it lets us talk about the periods or groups as a set easily. But it also lets us talk about a single element in terms of playing Battleship. For example, I could ask you, what element is in the 4th period, group 2. So I'd come over to my periodic table, I'd count down 1, 2, 3, 4. So I know my element's in this period. Then I know it's in group 2, so I'd go 1, 2. Where do the lines intersect? At calcium. So I can provide coordinates for any element in the periodic table using the group number and the period. Of the main group elements, and by main group, what we mean when we say main group are these representative elements, or these 1A, 3A, 4A, 5A, 6A, 7A, 8A elements. In other words, the elements in 1A through 8A. No B's allowed. Some of these groups have special names, and these groups with the special names have special properties. So we want to discuss the 4 colored groups here: alkali metals, alkaline earth metals, halogens, and noble gases. In addition to those named groups, let's review a couple other terms. Remember, the transition metals, or transition elements, are groups 1b to 8b, this gray sunken group here. Let's also talk about one other group of elements that we want to name, and that's your inner transition metals. Your inner transition metals are your lanthanides and your actinides, and those are the groups that you see down here. Remember, notice I said groups and not periods. Remember, technically, each one of these 2 elements is its own group, and these groups are actually located in period 6 and period 7. These lanthanides and actinides are given the collective name of the inner transition metals. And we won't spend too much time with those during the course of the semester. Matter of fact, most of the time we spent with these inner transition metals down here will actually be spent at the end of this chapter when we talk a little bit about nuclear reactions. We can also divide the periodic table into three really broad categories. That of metals, nonmetals, and those who don't want to choose sides, known as metalloids, or semi-metals. If you look at your periodic chart, hopefully you've printed one out, what you'll notice is that nearly all of them have a thick black line running down the periodic table, starting in the third group 3A right here, starting in group 3A, and staircase stepping down. This staircase step line divides metals from nonmetals. Elements that touch the staircase step, there, and there, are referred to as metalloids or semimetals. Now, it's important to realize that there is one very important, if you look at this list of metalloids here, you'll notice that all the elements touching this black line are metalloids, with one exception. The element right here. And that's an element that you're familiar with. The missing element is aluminum. And aluminum is very definitely a metal. And you won't find any disagreement on that. Unfortunately, what you will discover if you read different textbooks, different authors will actually classify some of these metalloids as not being metalloids. For example, I've seen several books that do not include polonium among the metalloids. Although I think they should, because after all, as Shakespeare said, neither a metal or non-metal be. And that's really, really hilarious if you realize that that quote's from Hamlet, and the person who said it's Polonius, and the element's polonium. Get it? All right. Moving on. The reason we divide metals from nonmetals is metals and nonmetals have dramatically different characteristics. Metals are shiny and ductile. They're good conductors of heat and electricity. They're the largest category of metals, largest category of elements, and all of them are solids except for mercury. Nonmetals are the exact opposite. Metals are shiny and ductile. Nonmetals are dull, brittle, and poor conductors of heat and electricity. On the other hand, because they're poor conductors, nonmetals make great insulators. Metalloids, on the other hand, split the difference between the two groups. They're better conductors than nonmetals, but not as good as metals, meaning that they're great for use as semiconductors. After all, if you look at that list of metalloids on the periodic table, you'll notice what element is present? Silicon, which is what we use for semiconductors in computers. All right, let's run through this list of elements and identify them as metals, nonmetals, or metalloids. First, we have sodium. Sodium is actually a metal. It's in group 1A, so it's a metal. Then we have chlorine. Chlorine's in group 7A, solidly in the non-metal category. We just said that silicon was a metalloid, or a semi-metal. Iron is solidly a metal, as one would expect, and carbon is the classic example of a non-metal. Chemistry is easy, life is hard, right? Because anybody can read the periodic table, once they know how. Match the elements to their description. Metals in group 4A. Get your periodic table out, locate 4A, and remember, they're only wanting metals. Reading 4A from top to bottom, you see carbon, silicon, germanium, tin, lead, and the next element is going to depend on your periodic table. But your line, your staircase step line, goes like that, huh? So that means you've got carbon as a non-metal in group 4A. You have silicon and germanium as metalloids. And this always makes me hungry for pizza, by the way. I'm going to really date myself by referencing an 80s advertising campaign. But Domino's used to have this little guy called the Noid. And whenever I say metalloid, I think of the Noid. And it always makes me hungry for pizza. But at any rate, so we're looking for metals. Since silicon and germanium are metalloids, they don't count. That leaves only tin and lead as our metals, which happens to be choice 1. Next, we're looking for nonmetals in group 5A. We look at group 5A, and going down the periodic chart, we've got nitrogen, phosphorus, arsenic, antimony, bismuth, and again, depending on your periodic chart, it's going to depend on the name of that last element there. Your dividing line goes under arsenic and around antimony. By the way, did you hear about the 2 elements that got a divorce? One of them had to pay antimony. Make sure you try the salad bar. At any rate, since that's our dividing line, that means that nitrogen and phosphorus are nonmetals. Antimony and arsenic are metalloids. And bismuth is going to be our metal representative. The question's asking for nonmetals, so we have no problem with that answer. Finally, they want metalloids in group 4A. Hey, I just erased that. That was the silicon and the germanium. Chemistry's easy, life is hard. Identify the element described by the following. So now you're playing Battleship. You're simply going to run your your finger down each of the groups and identify each of the elements. I'll let you do that without walking you through it and checking your answers on the next slide. I'm pausing here so you can read the answers and make sure they were the same thing that you got. And I'm sure there were because you're awesome. Which of the following is incorrect pertaining to nonmetals? Let's see. Do nonmetals typically have a low boiling point? True. They are found at the right-hand side of the periodic table. Well, let's see. Nonmetals are found on the right-hand side. Correct. They are not good conductors. They are poor conductors. So that's false. They're poor conductors, good insulators. And all I can say is about the colorful part, apparently somebody was really stretching to make a multiple choice question there, because colorful is really a relative thing. Many are found in the gas phase. That's actually very true. Just to talk about phases and elements in the periodic table real quickly, everybody in group 8A is a gas. So all those elements are gases. In addition, nitrogen, oxygen, hydrogen, fluorine, and chlorine are all gases as well in their natural state. So there are several gases among your nonmetals. By the way, you are responsible for knowing this. Let me write that again and write it a little bit neater. I'll bring it up again undoubtedly before the end of the semester. But let me write that very neatly. No! Remember that fluorine, chlorine, and group 8A elements are gases. Your nitrogen, your oxygen, your hydrogen, your fluorine, and your chlorine specifically are what is known as diatomic gases. meaning in their natural state, nitrogen loves itself so much it forms a molecule with itself of 2 nitrogen atoms. Same for oxygen, hydrogen, fluorine, and chlorine. All of those elements exist naturally as little molecules consisting of 2 atoms. For example, oxygen's 2 oxygen atoms bonded together, and therefore they're referred to as diatomic gases. And we'll talk about that again and remind you of it when we get to nomenclature.